Ladies and gentlemen, I would like to invite Professor Corneliu Marinescu to the stage to make their presentation about fifth energy source, energy saving.
Good afternoon. Introduction. Okay. I understood that I'm replacing a famous philosopher who was supposed to discuss, deal with things related to ecology. Also, fortunately, even if I'm not a philosopher, my presentation is dealing with related problems to this topic. Ecology, energy conservation are very closely related, as you will realize, I hope, during my presentation. Okay, the content of the conference is related to economical, social, and technological issues, energy consumption by sector will be introduced, followed by measures able to save, improve energy consumption in industry, in transport, in household and tertiary services, and at the end, some ideas related to the relationship between energy and efficiency and pollution, improvements able to be performed by recycling. Okay, nowadays we have to face some challenges, and they are listed here. They are mainly related to the very great number we are now mankind. We consist in 7 billion people, and to supply this population with energy is indeed a challenge. This is not the only one problem, of course, because to rise the energy production level is unfortunately associated with a dramatic increase of pollution level. So these two elements are working together, and here we have a problem, of course. And the third challenge is related to the fact that the scarcity of fossil fuels nowadays is rising political consequences. And I don't want to enter too much into politics, but the turbulence nowadays in the Middle Orient is related to the scarcity of fossil fuel supplies. Okay, I am scientist, I am teacher, I'm trying to not involve myself in politics, but sometimes we cannot let them apart. Okay, now the title of my conference was the fifth fuel. Why fifth fuel? Because you can see the big four supplies of nowadays consisting in petroleum, coal, nuclear, and alternative or renewable sources, for different reasons, are not enough. And some reasons are listed on the slide, isn't it? Petroleum, coal, nuclear are accompanied by pollution in different ways. And in inserting renewable energies into the electric grid are rising problems related to the instability. This is a natural feature of renewables. Sun and wind are not available full time, isn't it? Or they are, especially the wind is randomly blowing. So the grid is not able to ensure if the amount of renewables into the grid is rising above 20%, is not enough to ensure a stable supply. So the fifth fuel from this point of view is the cheapest, is the less polluting, is perfectly clean, isn't it? And also it is stable. Okay, when we are discussing about energy efficiency, we are thinking, isn't it, at the last level, at the user level. So end use efficiency is what we are looking for. We are interested to save. The idea is that using smarter technologies, using more intelligence, we will try to find ways, and you will see during my conference that there are a lot of room to save in this respect. We are trying to squeeze more work from the used electric and the other types of energy. Because this is, as I said, saving energy or energy efficiency is the largest, the cheapest, the safest, the cleanest, and so on. But it has some advantages, more diverse and less visible. So these are not quite politics, isn't it? So for this reason, it is a little bit neglected. And let's have a look, how can we improve this end user efficiency? How can we squeeze more work from a certain amount of available energy? Fortunately or unfortunately, the rising prices of the energy is working in favor of energy efficiency. Okay, let's see which is or which are the concerns. Creating energy by means of fossil fuels is accompanied by release of huge amounts of carbon dioxide. And this carbon dioxide is creating the so-called greenhouse effect. Greenhouse effect, if you don't know yet, there are some scenarios which are telling us if the CO2 is increasing, then perhaps the Earth will look somehow like Venus, 400 Celsius degrees at the Earth's surface. And this is a very important curve related to the CO2 pollution. This is a so-called killing curve. Killing is the sciences, not the effect. But who knows? Yeah? This is the killing curve which was raised in the last 50 years in Hawaii. So Hawaii is rather clean, isn't it? So no local sources are contributing to the CO2 development. And this is the curve. You can see that the level of CO2 rise from 310 parts per million to 390. And the question is this related to human activity or it is happening by random? The answer is also available in this magnified part of the variation. Annual, so this is an annual variation, as you can see. And when the level is high and when the level is decreasing, the level is high during winter time or after winter, when most of the population which is living in northern hemisphere is heating himself, is warming himself. And then during the summer, the level is, the summer in the northern hemisphere is decreasing. Okay, just a little bit. This is a slide which I recycled from my previous year presentation. And this is related to the population. The pressure, as I said, is done by those 7 billion people looking for energy. And this is the increase, this is the increase of the population in the last 200 years. From less than a billion 200 years ago to the 7 billion nowadays. And you can see that in the last 50 years, the population doubled, more than doubled. Okay, so we are here. And let's look which possible evolution we have. This is the exponential curve. So the population will increase as it's done till now. This is the logarithmic, this is a exponential curve. This is a so-called sorry, just a moment. When a population attains or a certain activity attains all its possible reserves, it is using the whole available resources, yeah? Then it is following the so-called logistica. Okay? This is the logistica. So we cannot supply more. Consequently, we will stop. And the third curve, the green one, is showing a sorrowful scenario. We have a certain population attained such a great number that already they started to be interested for predators. But we, mankind as a population, have no predators, isn't it? Too many deers, the population of lions will increase and will stabilize, isn't it? Will stabilize or will decrease the growth of the population. But when the enemies are too many, the population starts to drop. And the question is, who are supposed to be our enemies? And the answer is a rather sorrowful one. So we have met the enemy, and they are us. And this is related especially this definition to population increase. Okay, now coming back and analyzing which are the sources available for energy we need. This file is showing us that mainly our energy sources are oil, are natural gas, and coal. All of them are polluting a lot. And as you can see, mainly more than 85% consist in these dirty sources of energy, let's say so. And what remains here for clean energies is quite a little. That means hydro, and this is the small one, is renewable. Nuclear can be seen as a clean technology only for a while, if you are thinking that, okay, the wastes are lasting for at least 10,000 years. Now, those were the sources. How the produced energy is supposed to be consumed. And this pie is showing us the repartition upon different users. Industry is using around 30%, transport is using around 30%, and the rest is used by household and the tertiary sector, services. Okay, this is the production, of course, at EU level. We can see a little bit more, but you can see from here that agriculture, which was neglected in the first pie, is a rather small energy consumer. Now, let's go deeply into the analyze according to the three main sectors: industry, tertiary sector, and households and transportation. How can we save energy? Between 55% and 75% of the energy, electric energy, is converted into other types of energy by motors, by electric machines. Okay? And in these two pies here, you can see how this huge amount of energy is delivered to different type of consumer by means of the electric motors. At the left, the industrial sector. We have fans, we have pumps, we have air compressors, cooling compressors, conveyors, just these black small slides, and other types of applications. So, on the tertiary sector, again, we have pumps, we have fans, 40%, almost 40% here, refrigerators, air conditioning, conveyors, and others. What can we realize from these two pies? That variable flow of different types of fluids, liquids, and air, and gases, and so on, have a rather great share, more than 40%. So now, due to this big amount of energy, more than 55 until 75% of the electric energy are converted by means of the electric motors. Due to this, at the European level, certain standards were introduced related to the performances, related to the efficiency, final efficiency of the electric motors. Okay? And these standards are part of an eco-design project, ecology again, which aims to reduce the energy consumption and, of course, to reduce the pollution level. And here you have a diagram showing how motors are efficient for different efficiencies and for different powers. From the left, small motors, till this end, 90 kilowatts motors. As you can see, small motors are rather less efficient. So efficiency 3, efficiency 2, and efficiency 1. Okay, so there are different types. efficiency 3 were already banned in European community, in the European community. And here you can see why we have to replace less performant motors, less efficient electric motors with high efficient motors. Because during the lifetime of a certain standard asynchronous motor of 50 kilowatts, the energy cost is 98.7%. So each percent, the rest, the installation, the maintenance, and buying prices especially, are a very low amount. So each percent of saved energy from here, from greater efficiency, is going directly in reducing the costs and the consumption, of course, of energy. Okay? So this is important to know. And another factor besides the efficiency of the motors, which is quite limited, you've seen we can deal within a small range with the available efficiency of the motors, but and another important factor, a key factor, I dare say, is related to the introduction of power electronics. This is a rather new domain, and not only power electronics. Electronics, control, automation, this is a new developed domain. And it has a great potential. And the potential is listed here, referring only to the conversion by drives. Conversion by drives in industry, factory automation, transportation, home appliances. We can save a lot of energy using variable speed drives, which are conditioned by power electronics. Power electronics is in fact power conditioning equipment, and you can see that motors are consuming at least 55%, and the savings can be from 25 to 40% in reduction. And on the last column, you can see which kind of, but they are less important, which kind of power electronics components are involved in this saving. More spectacular and more important is this slide. In this slide, you can see a classical old design of a pumping application and the new design involving power electronics, and compare the consumption between the two. Let's have a look here. So losses are in the transformer very, very small. In the motor, quite important, but into the pump, which is this one, losses are rather big. And also in the regulating devices, I mean the flow regulating devices, throttles and waves, yeah, a lot of losses are produced too. Why? Because electric motors before power electronics were constant speed machines, yeah? And constant speed machines cannot regulate the necessary variable flow into the different industrial applications. By introducing power electronics, we can control the speed of the machine and control also the flow adequately. Again, power electronics is a perfect power conditioner. And here to the right, you can see how by introducing this power electronic variable speed drive component, we can reduce the losses. So in the transformers, the losses are the same. Power electronic converters are extremely efficient, more than 98%, 97%, it depends also, 99% nowadays. So losses are also very, very small. In the motor, losses are reduced because the motor this time will work in variable speed at less power consumption level, and the losses in the pump by working at variable speed will decrease too in comparison with this, the other. And of course, the throttle or the valve will disappear. The throttle or the waves which are consuming a lot. And if we are looking now back, we can see from 100% effective used power to ensure the flow, we are consuming in the old technologies 285% of energy, almost 3 times. By introduction of power electronics and controlling the speed of the motor by means of power electronics, we are consuming only 160%, almost half. Okay. Now let's see figures related to fans this time. Fans controlled by dampers, valves, and you can see here in 24 hours, if you are, this is a classical example. Here you have as a big supporter of your university, Caradenis, isn't it? So in metallurgical industry, in the furnaces, we need different levels of, in furnaces, of air, of oxygen, depending on the stage of the of the steel production. And these are ensured by means of the dampers or by means of variable speed drives. And you can see here what are the savings if we are using variable frequency drives instead of the dampers. You can see that for 50% we can reduce 4 times the energy consumption. For 60% we can reduce dramatically too. And at the end, considering such a working cycle, 2 hours for 50, 3 hours for 60, 6 hours for 70, this is typical for metallurgical industry. 6% for 80, 40, 4 hours for 90, and 3 hours full consumption. You can see that using dampers, the necessity of energy per 1 year is this figure. And using variable frequency, we can reduce the energy consumption almost at half. Not half, but almost very close. Of course, it depends on the operation time. Here you can see that introducing variable is not efficient at 100%. The inverter is also inducing some losses. Okay, this is a typical in chemical industries, is a typical look, typical photo for a pumping system. You can see here different pipes of different sizes, bends, valves, trying to, these are valves trying to control the flow, and so on. The idea is that in a certain enterprise, by redesigning, by introducing variable speed drives, the energy savings were, and this is an incredible figure, but it is real, the energy savings were about 92%. Okay? So what means old design with heavy insurance figures, coefficients, and what means a new design nowadays when we have computers and models and power electronics available to reduce energy consumption. So this is the big idea in industry. All the processes in industry converting electric energy, mechanical and other forms of energy were designed 20, 40 years ago, 60 years ago, when, as I said, power electronics, control electronics, computer modeling power, advanced materials, of course, were far from the nowadays values. And including all of them, this is a huge, huge task for your generation, of course, for your generation, to reduce energy consumption. And to reduce energy consumption, using all these new elements, you have to redesign all the equipment, And in this respect, okay, my suggestion is teams of old gurus and many young, forceful members of team could solve the matter in question with success. And of course, these are only words. If we cannot give examples, and this is an example of the last 15 years, Dow Chemical, an American huge chemical company, targeted saving energy efficiency in its activity, and in between 1995 and 2005, they invested $1 billion, and the reward was $9 million in energy costs. You can see there is a huge potential. They considered this potential, and they launched a new 10 years program in which they targeted another 25% energy consumption saving. Okay, transportation. Transportations are consuming 1/3 of the energy, and they are responsible to a huge amount, 25% at least, of CO2 production. And besides CO2, we have CO2 has sulfur dioxide, we have particulates, we have certain chemical effects when the weather is warm, like now in big towns, in cities, which very dangerous effects. Okay, half of the emissions are due to passenger cars. Due to these figures, a scenario considering everything maintaining the same parameter is showing that in 2050, the level of pollution will double. Of course, doubling the level of pollution is something you cannot accept. Here you can see which is the consumption of energy by type of transporter. Ships of different levels for 1 kilowatt can transport 1 ton of material, 75 kilometers, 60 kilometers. Meanwhile, by rail, the journey is shorter, and by plane, of course, we cannot make a kilometer with 1 ton of material transport. This is a graph showing this distribution between consumption and speed, because this is a big problem when we are transporting different materials and passengers too. So freight and passengers are plotted here, considering costs of energy, which is in fact consumption of energy. And you can see supersonics are worse from consumption point of view and very good in terms of speed. Here we always have to consider this dispersion between consumption, this relationship between consumption and energy costs and speed, of course. It's a compromise between speed and energy, and we have, in the case of tankers and trailers and container ship and trucks, we have the advantage of the economy of scale. Meanwhile, when we are transporting passengers and sensitive merchandises, we have speed as the most important parameter. Anyhow, transport operators will try to have a compromise between speed, which is rewarding in overcoming distances, and energy, which is rewarding in cost, isn't it? So also here the compromises will vary in time related to the fuel price. And the fuel price, if it is fossil fuel, if it is gas, petroleum, of course, will increase in the next time, in the coming times. Okay, there are different ways to improve the cost in this respect. So here a key procedure is intermodalism. How can we combine different type of carriers in order to reduce the cost and the time between the supplier and the end user? Air freight is, of course, highly energy intensive. So here we have to take care in such a case, and of course the companies are taking care. And another factor related to the speed this time is that higher speed means higher energy consumption. And this is done mainly, this is happening mainly due to the friction between the vehicle and the air. And this is an exponential curve again related to the friction between the vehicle and the air. And you can see that as the frictions are increasing, meanwhile the other losses related to tires, brakes, and so on, the remaining energy available to rise the speed is smaller and smaller. This is on the one hand. On the other hand, we have somehow to install a speed limit, because the exponent here in this exponential curve, the exponent is the power of 3, is 3. Okay, so we have somewhere to limit our speed, 90 kilometers per hour, 100 kilometers per hour. Here we have the speed in miles, to avoid this last tail effect of the speed. Especially when we are discussing about cars, about passenger transport, here speed limiting is not quite pleasant in order to limit the consumption. But in the same time, using classical internal combustion engine machines is expensive from the pollution point of view. So the idea is, of course, electric vehicles, EVs. Now let's see, have they any future? Because still internal combustion machines are quite spread, isn't it? Now let's have a look what is the efficiency, because you see nowadays models, gas is still cheap, so nowadays models are also cheap because they spent all the research expenses, so they are able to lower the cost. Let's see if they will be replaced. And these figures here related to final efficiency of each vehicle are, I dare say, and lighting the future of the electric vehicles is very bright. So more or less, they start to be compulsory from the point of view of price, oil price, and pollution. And here you have, this is the final efficiency, starting not from the pump, starting from the crude oil, yeah? The final efficiency, considering transportation, industry producing gas and so on, the final efficiency is between 15 and 20%. Okay? This is the hybrid case. The hybrid case is rising a little bit. Hybrid vehicles containing internal combustion engines and electric motors. Okay? Is rising a little bit efficiency because here we can recover some amount of energy and fix the working speed of the internal combustion machine at its maximum efficiency levels. These are plug-in hybrid electric vehicles. That means they are able to charge their batteries by plugging during the nights, especially the battery into the mains. And this is the electric vehicle efficiency. And comparing the figures between internal combustion and hybrid electric vehicles and electric vehicles, one can easily realize that the efficiency, final efficiency, starting from the electric energy source, yeah, of the electric vehicles is 3 times higher, is 2 times higher than 3 times higher than internal combustion and hybrid. So obviously this is the future. There is a research based on producing electric energy on board by means of fuel cells, but the final efficiency of the cycle producing hydrogen, converting hydrogen back into electricity is also small. So the future is net in favor of electric vehicle based on lithium-ion, especially batteries. Even if lithium-ion technology is still under development, is not an established development. And next slides are analyzing the pollution, the effect upon pollution of using electric vehicles. Okay, you can compare here which is the CO2 pollution induced by internal combustion engines based on gasoline or diesel, and which is the pollution of electric vehicles using classical coal-fired electric energy. The level of pollution is high. No efficiency is resulting in terms of pollution using coal-based electric energy. But if you are using gas combined cycle, so producing energy by consuming gas is a resource which will last for at least 100 years. Using energy produced by gas is beating gasoline, and using renewable energy is rewarding at least twice in terms of decrease of energy pollution, or based on carbon dioxide. If we are discussing about pollution based on sulfur dioxide, which is responsible for acid rains, isn't it? Then again, if we are comparing gasoline and diesel-based with coal electric energy, of course, is not an advantage of electric vehicles. But if you are comparing with gas combined or wind and why not photovoltaics electric energy, okay, is again twice more clean to use electric vehicles instead of. Here you have other transportation means. Again, what I told you before, that redesigning is a very important aspect. You can see here by redesigning the aviation vehicles, we can improve the efficiency with 30%. By redesigning the ships, we can improve the efficiency with 35%. The rest are organizational, operational alternative, or to use biofuels, hydrogen, and so on. They are less involved in energy saving from this point of view. Okay, and this is another example. We have to work with examples, not to only with words. You know that it was a big fight between Boeing and Airbus, the biggest planes designed in the last years, trying again to lower the consumption on the scale effect by designing planes able to carry from 350 to 500 people in the same plane, okay? And from this point of view, the two designs between, the fight between Boeing and Airbus was won by Airbus because its vehicle is 20% less consuming fuel in comparison with all. When you will design, you engineers, if are here, design new products, take care on this aspect. At the same costs, those planes which are able to consume less energy are more competitive. Here is another example which is linking the next chapter, lighting with LEDs. And you have an example how new technologies, in this case lighting by means of LED emitting diodes, can replace all technologies. In the case of traffic lights, LED traffic lights are using only 12% from the energy used by the replaced incandescent bulb lamps. So 12% is an interesting figure, because there are also other parameters of interest. For example, when an incandescent bulb is broken, it ceases to work, to enlight, isn't it? Meanwhile, a LED matrix, if 1, 2, 3, 4 LEDs are falling, the other, let's say 20, are still operating. So from this point of view, again, it's a plus for the LED traffic lights. And the calculus done, the computation done at the United States level are showing that if they are replacing these traffic lights in the United States, a great country, isn't it? That means because traffic lights are running 24 hours a day, full time, 7 days a week, okay, replacing them with LED signals will save 3 billion kilowatts hour, $240 million at the electricity cost in the United States. Or that means to not build or use in other purposes a hydropower station of 340 megawatts, a huge one, isn't it? Okay, now, as I told you, replacing incandescent bulbs with LED means also saving in our houses, but the technology is still under development at this level, is not yet okay, not from LED's point of view, from the circuits associated to LEDs, is not under, it is still under development. It's not established technology yet. Okay, so I switched to households and services, tertiary sector, as I said. Here we can see in our houses which are the appliances, which is the consumption of energy in 1 year. Yeah, these are the appliances, the consumption, and here up the price related to the consumption in dollars. And you can see here there are small consumers, energy consumers, but there are big energy consumers like pumps, again, refrigerator, which is also a pump at the end of the machine, washing machines, dryers, heaters, these are big consumers. So they are the target for redesigning, for replacing, for an efficient use of energy. We can organize from this point of view our activity to try to save energy by organizational measures. No cost, but we have to change our habits, isn't it? What are those? We can switch off, not let them switch on in idle mode. Dishwashers, PCs, monitors. We have the possibility to lower the temperature because it's stupid of hot water. It's stupid to produce hot water with a lot of energy, then mix it with cool water to adjust the temperature. Why not to use at the adequate temperature the hot water? Okay, unplug these electronic devices, coffee warmer, and so on. Yes, to use cold water for those laundries which are not asking hot water in any instance. So these are measuring, requiring a small investment. You can see here, but they are not waiting for us. Computer industry is not waiting for us to switch off when it is not in use. They are already producing devices which are requiring energy according to the needs, and even switching off the computer where no power is required, when computing power is not required. I don't remember exactly Intel last chip which is doing these things. Okay, replace incandescent bulbs. Okay, plug unused chimneys during winter. Check for insulation and gaps, of course. And if I show you at the beginning which are the big users. If those appliances are energy users, those appliances are old, try to replace them with the latest available high efficient level components. That means refrigerators, air conditioners, washing machines, and so on. And houses, of course, have to use double or triple glazed windows in order to they are expensive, but they are rewarding in terms of energy. And here, that was industry, and this is how power electronics can help us to save energy by computers, okay, avoiding standby, by power supplies, also for computers, rising them in efficiency, those power sources, attached to computers, so not let them to operate full time, and also for lighting devices to use dimming elements in order to control properly the flow of light according to the needs and not switching directly at their maximum power. Okay, here you can see how can we build houses. This is just related to PVs, photovoltaics, okay, that's why I introduced it. I'm dealing with photovoltaics. So you can see how the sun is moving its position according to the season. This is the trajectory on December, and this is trajectory on June. So we can attach to our houses such sun space construction, this one, okay, which with a special geometry can allow the sun to enter during the wind and heat our house, and avoid heating the house during summer when it is very hot and you will need perhaps air conditioners and consume energy using air conditioners. So we can save by clever designs a lot of energy in our houses. And another important task is demand response. So this is very important. This is related to energy storage, to renewables, to grid forecasting, where we are introducing renewables. It's a big issue, but it's a complicated one. But with now today technology, we can create models. We can create powerful models to which we can create, with which we can create such a demand response adequate to limit consumption during, especially in peak hours, when we are introducing, sorry, I received the bill, okay? So we can limit the consumption during peak requirements and delay them, dispatch later, later when the supply is exceeding, the power supply is exceeding the requirement. And we are smoothing in this respect the demand curve, the load curve of the grid. And this can be done automatically, and doing it automatically means we can create a so-called smart grid. So this is a big issue in research nowadays in energy transmission. So, okay, last part I will pass, recycling. By recycling, we can save a lot of energy and avoid a lot of pollution. Okay, so aluminium, recycling aluminium, for every kilo recycled aluminium, we can save 14 kilowatt hours of energy. We can produce only, we can save 95% of CO2, which is created when we are extracting from the ore the 1 kilo of aluminium. The same in the case of the steel. We can save 75% by reusing recycling steel. We can reduce air emissions, pollutant emissions, 85%, and water pollution, which is again another big issue I had no time to deal with 76%. Recycling copper, means we can save 90% of energy and reduce a big amount of associated CO2. Recycling paper, here the figures are still under debate, but you can see we can save between 40 and 75% of energy by recycling 1 ton or 1 kilo of paper, and reducing the pollution with 35% in water pollution, and in air pollution 74%. And I have to add here, we also can save a lot of trees, which are contributing to pollution reduction, isn't it? So they are not mentioned here, the trees. use as raw material to produce paper. Also, recycling plastic is rewarding from energetic point of view. You can see here how much energy, okay, mega British thermal units is a measuring unit this time. And I arrive to the conclusions. Highest return, energy saving is the highest return, lowest risk investment available. And it is limited less by technology and economy, but more by wrong culture and lack of imagination. We have to change many things in our mind from this point of view. At our home level also. I have no time to debate on it. Okay, so innovative designs, technologies, policies, and marketing methods are increasing the energy efficiency. And they are increasing them faster than we can use up. So here is a favorable race from this point of view. New knowledge, new technology, and new living habits will be needed. But it is a difficult task to introduce new habits, isn't it? That means creative adaptation and innovation with change of social and human habits, and this means education, okay? Education. Intelligent, high-tech, local and global energy management means to reduce waste, to improve efficiency by intelligence. And we can do this easier than the first educational target. Energy conservation and regeneration have very huge potential, particularly in industry, but also in the other domains, okay, in other sectors. And at the end, if saving energy is so important, why don't we hear more about energy efficiency? And the answer, I called it the red ribbon effect, because one European commissioner on science realized that, okay, politicians are not interested in promoting energy efficiency. No, like in the case of big, huge investments, plants, power stations, everywhere politicians are under TV cameras cutting red ribbons. For them it's important. So, because in saving energy, there are no huge plants, there are no huge investments, no red ribbon to cut. So that's why perhaps we are not hearing enough, by my opinion, enough about energy saving. Thank you.
We appreciate for his nice presentation, and I would like to invite lecturer Caner Özcan to give their gifts.